Hey, welcome back to Advanced Mechanics. Today we're going to be looking at another Lagrangian example. This is a pretty simple case. You have a rolling disc and it's attached to a spring, and the spring will oscillate back and forth, which will cause the wheel of this rotating disc right here to go back and forth. And we want to know what the equations of motion are going to be for this object right here. So the first thing we want to do is figure out what what is our kinetic energy. To do that, we need to first look at this object right here, and we need to determine what the moment of inertia is. So the moment of inertia for a solid disk is equal to a 1/2 mr squared. And then also, because we're going to be talking about rotational kinetic energy, we might as well look at this omega term, which is going to have a tangential component to it. And we can say that omega is equal to the v tangential divided by r. And since we're going to be using the generalized coordinates here, let me make that a little bit more clear. Since we're going to be using our generalized coordinates here, we can say v is really the same as x dot. So we end up with x dot divided by r. Okay, now we can move on to talk about our energies. We're going to have translational energy as well as rotational energy. So the kinetic energy, Ke, or T, is going to equal 1/2 mv squared. That's the translational energy of this. The spring doesn't have any mass, so we don't need to worry about that. Plus 1/2 I omega squared, and that's the rotational kinetic energy. And we could rewrite that as 1/2 mv squared plus 1/2 I, which is 1/2 mr squared, times omega, which is x dot divided by r squared. And then the r's will cancel out, and we can clean this up a little bit, and we end up with the kinetic energy, which is T, is equal to 3/4 mx dot squared. All right, so that's our kinetic energy. How about our potential energy? Well, the only potential energy we have here is due to the spring. So the potential energy is going to equal 1/2 kx squared. Pretty straightforward. Now we can plug it into our Lagrangian. Let's put that up here or down here for now. So the Lagrangian is just the kinetic minus the potential, and that's going to be 3/4 mx dot squared minus 1/2 kx squared. Once we have this, we can start looking at our Euler-Lagrange equation. We just need to do it for one because there's only one variable, x, here. So the Euler-Lagrange equation tells us that I'll write it this way, d over dt of the partial of the Lagrangian with respect to x dot is equal to the partial of the Lagrangian with respect to the position instead of the velocity term. So that's a Lagrangian. We need to figure out this, and then also that. Let's look at the, I don't know, which one should we look at? Let's look at this one first right here. So where can I write that? I'll put it up here. I think there should be enough space for that. We have d dl of dx, and that's going to equal, let's look at our Lagrangian here. There's no x term here, so we don't need to do that. The derivative of this with respect to x is just going to be 2 times 1/2 kx, which is just negative kx. All right, we're done with this side. Now let's look at this side right here. So we have d dl over dx dot, and that's equal to, so looking at our Lagrangian, this is the only one that has an x dot here. You bring the 2 to the front, and it's going to become 3/2 mx dot and then we have to take the time derivative of this. So d over dt of 3/2 mx dot is going to equal 3/2 mx double dot. So now we can write down our Lagrangian. It's going to be this term is equal to that term. We have 3/2 mx double dot is equal to negative kx. And what can we do from here? We can distribute all of this term to the other side here. And we have x double dot is going to equal negative 2/3 k over m x. So if we want, we can make it a little bit nicer and bring this thing to the other side. And we end up with x double dot plus 2/3 k over m x equals 0. This is a differential equation, and it's a pretty simple differential equation as well. This is just for like a harmonic oscillator. The solution to this, or I guess I could actually just take one more step and say that omega is going to equal the square root of 2/3 k over m. And so if we rewrite all of this term in terms of omega, and that's just going to be x double dot plus omega squared, x equals 0. And you've seen this one from mechanics before. The solution to this is going to be simply x as a function of t equals x max. X max. What are we going to do? We're starting from not equilibrium, so we'll use cosine. Cosine of omega t, and there is no phase shift. So that's what we have. And if you want, you could just put this back in there as well. So that just becomes x as a function of t equals x max cosine of the square root of 2 over 3 k over m times t. And something interesting that you might want to note is that if this wasn't a wheel here, let's say if it was a block, then there wouldn't be any rotational motion. It wouldn't have a moment of inertia. So if I were to equal 0, then omega would be simply square root of k over m. And that's the harmonic oscillator for just a block on a spring instead of a wheel on there. Okay, so our final solution is, well, this. And it's pretty nice to get this value by simply just using a Lagrangian and getting our value to be that. Okay, so that's it for this one. I'll see you in the next one. Adios.